Question number 11. A solid sphere of radius r made of a material of bulk modulus K is surrounded by a liquid in a cylindrical container. A massless piston of area A floats on the surface of the liquid. When a mass m is placed on the piston to compress the liquid, find fractional change in the radius of the sphere. Okay, so first we are assuming that here we have that container, and in that container a solid sphere of radius r is here. Okay, so here we have some liquid, and here we have a piston, a massless piston, right? And these all are liquid in that container. Okay, so initially the radius of that solid sphere is r, so we are assuming, so the volume of that sphere is 4/3 pi r cube, right? Now when in this liquid, in this piston, basically we are placing a mass. So again I am drawing this. Now we have some mass m on that piston, which is here. Okay, so whenever the mass m is placed on the piston, that means some pressure is applied, right? So whenever we have some pressure here, so we know pressure is equal to force upon area, right? And here it would be mg upon area. And whenever this pressure is applied, and we know that this pressure is applied equally in all sides of the liquid, right, from the Pascal's law. So now we can say that means the volume of this solid sphere is reduced, and whenever the volume of that solid sphere is reduced, that means the radius is reduced as well. So we can imagine, so the volume is v dash. Now we are assuming that the volume of that solid sphere is v dashed, and the radius, suppose r dash is the radius, so this is r minus delta r. Okay, so this v dashed, this would be 4/3 pi r minus delta r cube, right? So from here only we can simplify this, as we can take r cube as common, and 1 minus delta r by r whole cube, and we can apply the a minus b whole cube formula. So 4/3 pi r cube, it would be 1 minus 3 delta r by r minus plus of 3 delta r by r whole square minus of delta r by r whole cube. So we can neglect this two term because these are very small, so we can neglect this two term. So the final would be v dashed is 4/3 pi r cube 1 minus delta r 3 delta r upon r. Okay, so this is our v dashed. Now v is 4/3 pi r cube, so we can write this as v 1 minus 3 delta r upon r. Okay, so from here we can say, so the change in volume delta v is equal to final volume minus initial volume. So final volume is v into 1 minus 3 delta r upon r minus of v, so which is equal to minus of 3 delta r by r into v, right? So now we have the change in volume, we have the pressure, the amount of pressure, and we have v as well, right? So we can calculate the bulk modulus from this. So we know bulk modulus K is equal to P upon delta V by V. Now we always, whenever we calculate the numericals of the value of bulk modulus, we always take the positive value, right? But in general, in equation we have a minus here. Okay, so we can put this minus. So this is P is equal to mg by A. Delta V is minus of 3 delta R by R into V divided by V. So V will cancel out. This minus will cancel out with each other. So we'll be having mg upon A by 3 delta R by R. So from here we have to calculate delta R upon R, which is equal to mg by 3 Ka. So here the final answer would be, so we have to calculate the fractional change in the radius of the sphere, which is mg divided by 3 Ka.